Hi, so my name is Morriel. I'm a first-year PhD student working under Professor Spasojevic in WINLAB. I'm going to be presenting about low-resolution ADCs, specifically with application for ultra-high bandwidth. I'm going to go through some background and motivation, and then talk about some of the areas of research I do, and then the technologies that this supports going forward for 5G and MIMO, and a lot of other really interesting fields. So to start, I think there's a few takeaways that are really important, especially when you talk about low-resolution stuff. The first one is obviously less is more, right? Why do something with high precision and high resolution if you can get away with doing the same thing in fewer bits and with the low resolution device? The second thing is, like the physicist Richard Feynman says, right, there's always more room at the bottom. So why not try to make things smaller and more efficient? If every device with an ADC right now can get the same performance with fewer bits, you instantly save a huge amount in size, weight, power, and cost across, scaling however many devices you use. So obviously it's a worthwhile thing to look into. And lastly, there's a lot of unexpected places that we can find value. I think a lot of people discount ADCs as kind of a marginal or trivial part of a lot of different systems. And I think I'll try to argue here that there's a lot more interest in them that people should explore. So to start out with the background, where does quantization show up? I think when a lot of people think about the quantization process from the analog domain to the digital domain, the first thing people think of is probably with digital data. You compress digital data like images here, have a high resolution image and it goes to low resolution. But also it shows up in a lot of physical systems. So if you think about audio processing, you have some sound wave that goes through, MEMS transducer, and it gets turned, it goes through a whole lot of analog processing parts. But before you can actually do anything with those samples, it has to get quantized. So there's ADC shows up in most microphones. And then obviously in pretty much every RF system, you have a whole lot of stuff that goes on the front end in the transceiver. You have a whole, host of RF components that people do a lot of time optimizing with the LNAs and mixers and RF filters and antenna. But a lot of people kind of forget that before you do anything in the DSP side, it has to go through an ADC. So these are pretty ubiquitous components. So the project that I'm on is funded by the Office of Naval Research through an STR Phase 2 contract. Really, the premise that we got hired for was they have a really low resolution, really high bandwidth ADC, and they're trying to find ways to linearize and optimize it for spectrum sensing applications. So this is kind of a uniquely hard problem because how do you do a lot with this really wide bandwidth you have, but your dynamic range is extremely limited because you're only working with a few bits. So let me get into what that means, right? Why should we care about quantization in the first place? Obviously, it shows up in a lot of places, but what does it actually do? If you take a look at these two images, one of these is a sinusoid that was quantized to 16 bits. Another one is the same sinusoid quantized to 12 bits. You probably can't tell the difference at all, right? I mean, they look pretty much identical. And I think this speaks to a lot of the assumptions people make about ADCs and the quantization process. Well, it's pretty much negligible, right? We'll just ignore it. We have some analog signal and it shows up in the digital domain and it looks roughly identical. And I think, maybe if people think about it one step further, we get into some of the common assumptions behind what ADCs do. And you say, well, as long as you stay within this so-called linear region outside the saturation rails of the ADC, it's approximately linear, it's a pretty linear transfer function. And you assume that it maybe, if you want to get one step further, it injects some small additive noise. But like we saw before, right, the 12-bit sinusoid looks pretty much identical. So people say it just raises the noise figure slightly of the system. And in general, I think people think ADCs are not that interesting. It turns out that all three of these assumptions are false. First, even within this linear region, the transfer function is decidedly nonlinear. And you can see that these hard steps actually introduce a lot of distortion. The second thing is that the noise is not even additive. In fact, it's a deterministic function of the input. So a lot of the existing models for ADC are not even really an accurate characterization of what they do. And hopefully I'll be able to convince you that they're interesting, right? Otherwise, this talk is kind of a waste of time. So where things really get interesting and we start to see some of these effects show up is at really low resolution. This is the same sinusoid quantized to 3 bits or 2 bits. And you can see here, obviously, if you know it's a sinusoid, you can still make out the shape. But there's clearly a lot of information that's been lost. And recovery of that information is a non-trivial process. And if you look at the spectral domain, right, this is now the FFT of each of these. If you look at the power spectrum, you can see that at high resolution, like 12 bits here, that it looks like a tone. But at 6 bits, you start to see some raising of the noise floor. And at 3 bits, you get these really strong nonlinear harmonic distortions. We call these harmonic spurs. And these are a really significant problem for trying to do anything with your data, because this is a really strong distortion that is not just the characteristic, increasing of the noise floor. There's a lot of other stuff going on in the spectrum that really modifies your signal a lot. So as far as motivation, obviously, I've shown you that at low resolution, we distort our spectrum quite a bit. Why would we want to do that, right? Why would we ever want to make our spectrum look so distorted? The real answer is that high resolution ADCs are very expensive, not just from a cost standpoint, but their implementation requires a lot of power, a lot of area on the chip, and a lot of size. So obviously, the low resolution ADCs are largely been ignored because such a coarse quantization introduces all the distortion I showed you. But if we can find a way to get them to work despite that distortion, there's a huge number of benefits to getting away from this high resolution ADC background that we Obviously, reduced power consumption. You have fewer parts that you have to, fewer comparators, smaller die area on chip, cheaper manufacturing implementation. And not only that, but the entire digital front end, right, back end that has to process those samples gets a knock-on effect because now you have fewer bits per sample you need to process. So the entire digital complexity gets reduced in your DSP domain. So you actually get later savings. And obviously, because of that, we can support increased bandwidth. Because you have to spend less time on each comparator and you have a faster sequential design, you can support these ultra high bandwidth applications uniquely with low resolution. Where this really comes in handy is in MIMO. So this is an example of, from a paper I found, this is a 5G MIMO transceiver proposal. These guys want to put 64 antennas in a MIMO array, 4x16. So obviously, if you have 64 antennas, each of which has its own ADC, and you want to have each ADC at high resolution, like 12 bits, right? Assuming, let's say, it's a flash ADC, you're talking about 250,000 comparators on your chip, right? Good luck. So if we can do the same thing, but with 3 bits on each ADC, now you're talking about less than 500 comparators. So obviously, for MIMO applications, the scale is really significant, and doing things in low resolution is very beneficial. And the other application is because low resolution can enable really wide bandwidth, you get really interesting results when you look at things like direct sampling receivers, which are really popular, rather than going to an IF and then sampling with a smaller bandwidth. These really wideband applications can just direct sample your signals at baseband. And then the reason we want to direct sample is because there's a lot of stuff going on in the spectrum nowadays, right? If you want to receive simultaneously ultra wideband signals and look at some satellite uplink and see Wi-Fi and see Bluetooth for really wideband spectral estimate and good spectrum sensing, you need a wideband receiver, and low resolution allows you to do that. So what are sort of some areas of research that we do that allow us to kind of support these wideband results? The first one is, I think the simplest implementation is what's called a lookup table. So in principle, you take your original signal in the analog domain and you quantize it very coarsely, and you result with a digital signal with very low resolution. You can just take those past few samples and use them to index an estimate of your signal. So effectively, we're using a lookup table to perform some kind of spectral estimation and use that to update the current digital value. So this block diagram looks a lot more complicated than it is. We're just basically creating an estimate of our signal using the past few digital outputs and then indexing into a new updated value for that signal. And what we can do is that maintain the same resolution, but just by shifting a few of the values around, we can really optimize the spectral performance. And you can see here a plot from our paper where you have a tone before that had a very limited dynamic range. And you can see that a lot of that distortion aliases back into the spectrum and shows up all around where your tone is. And it makes it very difficult to tell what's going on. With just a simple lookup table that can be implemented with a lot of memory efficient ways entirely in the digital domain, we can totally improve our spectrum. And now it sort of looks more like a conventional, a little bit raised noise floor that we can work with. The advantage of this approach especially is because it's entirely digital. So you can take your existing analog hardware, your existing ADC architecture, and then in your DSP domain, right, take your wireless modem and implement a lookup table entirely on an FPGA or entirely in the digital side, which obviously is a lot lower cost and implementation complexity than having to take an analog high resolution precision measurement with a high resolution ADC. So a lookup table is a very attractive option. The disadvantage of this approach is that for higher resolutions, the memory size that's necessary to get a good signal estimate blows up exponentially. So these are kind of uniquely used for low resolution ADCs where we can try to constrain the memory as much as possible. But obviously there's a trade-off where if you want a really good signal estimate and you want to update it accurately with the lookup table, the digital side of your domain increases to support that. So somewhere in the, somewhere you have to pay the price. But this advantage of also with this is that it can also support nonlinear ADCs. So if your ADC is not only no low resolution, but it has a lot of distortion in the manufacturing process due to nonlinearities that are built in, this can also compensate for those. So nonlinear ADC linearization is a really big field where post-correction typically requires a lot of digital complexity. This is one way to implement both of those at the same time, get a little bit of extra savings. And some other work we did found that we can actually get really precise spectral estimates using some other signal processing techniques. So this is one approach. Another one is what's called dithering. This is the most popular for low resolution ADCs, and there's a lot of literature on this. The idea of dithering is basically that you take whatever original analog signal you have, and you add a small amount of independent noise to it. And that noise has a very specific distribution that we've designed. And then you can either subtract it out later in the digital domain, which is called subtractive dithering, or you can just leave that noise in and take a look at the resultant quantization. This is called non-subtractive dithering. And you might be thinking, why would we want to add more noise to our signal, right? If you remember before, a lot of the distortion shows up because the ADC with a coarse quantization, it has a deterministic transfer function. Instead, ideally, we want the noise to just be a stochastic variable, which we add on top. And so dithering kind of allows us to mimic those properties. You can see on the left our coarse deterministic quantization, which, while optimal, right, in terms of maximizing how much it looks like a sinusoid, has really undesirable spectral properties. And you see a lot of these harmonics show up that really distort our spectrum. If we have non-subtractive dither, we just add a small amount of noise prior to quantization, we can break up those correlations. The penalty we pay is an increased noise floor. So the spectrum looks a lot better, but in terms of a mean square error sense, this is actually slightly worse performance. So we raise the noise figure, but in spectral applications, this is really desirable. And lastly is subtractive dither, in which we achieve the same results of decorrelating the error from the input signal. But again, we pay a little bit of a noise penalty. It's just a lot better than non-subtractive dither. And in fact, you can control the error moments such that it's minimized. The real downside of subtractive dithering is that it's very difficult to implement in practice because you need a cohesive and coherent digital domain representation of the analog noise you're adding. So subtractive dithering is ideal, but kind of avoided for a lot of reasons. So a lot of our research focuses on optimizing non-subtractive dither to minimize this noise penalty while maintaining these desirable spectral properties in conjunction with these other techniques I described, like lookup. Another thing that we really look into quite a lot is called non-linearity injection. So a lot of ADCs, if you look in the red staircase that I showed you before, is a so-called linear transfer function, where it looks like the analog function as optimally as possible, and it tries to track it as well as you can. And on the left here, you see a block diagram for a conventional flash ADC. This is the simplest ADC architecture. It just takes the analog signal and it compares it to a bunch of different voltages. And then you get a 1 if it's above or a 0 if it's below, and you can convert that to a digital value. It's just a whole bunch of comparators in a row. So what happens is when you actually go to manufacture a flash ADC, we usually want to have the reference voltages exactly equally spaced apart. So you get the same width of each bin, right, for each bit. The issue is if there's even a small manufacturing tolerance on these resistors, they're not going to be exactly the same width, right? Your resistor ladder is going to have slightly different resistance values when you go to manufacture it. And the result is that your ADC transfer function will be nonlinear. And you can see here in the green an example of a nonlinear transfer function where you have some variation from the ideal one. So a lot of people try to compensate for this nonlinearity, but in fact, the optimal nonlinear transfer function can outperform a linear one if designed appropriately. So this is kind of an unintuitive result, but if you know some characterization of your input signal, like let's say you know the distribution of the input you expect is Gaussian, for example, then you can actually optimize what these levels and resistances should be to get a better estimate with your quantization, which is shown in the green, than just a perfectly linear ADC. And so one of the classic examples is what's called Lloyd-Max quantization, which minimizes the mean square error for a given distribution. And this is an example of what a Lloyd-Max transfer function would look like in the green for a Gaussian input. So it turns out that for a lot of other types of signals, you can actually optimize this even further. So rather than optimizing for mean square error, for example, we can optimize for bit error rate in an RF application. And then it turns out you get a new different nonlinear transfer function. So by injecting nonlinearity into the ADC, we can further improve the spectral performance and also just the RF performance. If you care about error vector magnitude for an OFDM signal, OFDM signals we can usually approximate as being Gaussian distributed because of central limit theorem, and then you can optimize an ADC specifically for that application. Rather than just saying, we bought an ADC chip from analog devices and we put it in and it was linear and this is the performance we got. I argue that with low resolution, you can really crank out a lot of extra performance by being very careful about how you select these transfer levels. And the last thing we can do is specifically in ultra wideband application, or I should say ultra high wide bandwidth, not specifically UWB. We can oversample our signal and then use that to reduce some of the distortion. So on the left here, you see there's a tone around 30 megahertz and it's sampled at 100 megahertz. So the result is that a lot of the distortion alias is in, right? So when you quantize something, you get these, like I showed you, a lot of these harmonics and this coarse quantization. The digital harmonics are going to alias all over your spectrum, and you get to the below and above your frequency of interest, a lot of distortion. By oversampling, less of those harmonics alias back into the band you're interested in. So if you know that you only care about, let's say, a narrow bandwidth, you can actually sample at a much higher bandwidth with this coarse quantization, and then more of these distortion terms show up, outside, right, out of the way of the signal you're interested in. But then obviously we need to get rid of them. So we can take this oversampled signal and then try to post-process that distortion out to concentrate it on our narrow band. So naively, right, the simple approach is let's just low-pass filter for the signal we're interested in, which is like sync interpolation. But that's kind of hard to implement for ultra-wide bands because how are you going to do an FIR filter with this many taps if you have to process these samples with like 1 picosecond between them, right? It's very hard to implement digitally. So a simpler approach is time averaging, which is called like box interpolation, but this has worse spectral properties. And then the most advanced approaches that recent research areas have shown are actually using Lagrangian interpolation methods and really advanced ways to try to recover an optimal estimate of your frequency of interest, given that it's band limited and you've oversampled by a lot. So specifically for these wideband applications with these coarse quantization, there are some really optimal interpolation methods that are a lot more complex to implement, but which can really crank out a lot of performance from these systems. So this is an example of a block diagram from Silicon Labs where basically they take an ADC and they add some dithering and then they oversample it and then they average out some of the noise, right? So if more of the noise falls out of your band of interest, you can average that out over time and get a better estimate. But of course, the disadvantage to this is that you have to oversample. And in fact, the improvement in resolution that you get is a function of how much you oversample by. So for example, if you have this is an excerpt from a paper that I thought was really funny, I included here. If you have an 8-bit ADC and you sample at 1 gigahertz, and you want a 22-bit measurement out of that, you can get a 22-bit accuracy from your 8-bit ADC. You just have to downsample by a factor of 1 billion, and your effective rate becomes 1 sample per second, right? So obviously that's an impractical example, but if you really want to crank 14 more bits out of your ADC, you can do it. You just need 1 billion times the bandwidth of your signal. Obviously, in our case, we're looking at, let's say, a 3-bit ADC, and we want it to work like a 6 or 7-bit ADC. Now it becomes more reasonable. We oversample by a factor of 64 or 128, and suddenly these implementations become a lot more realistic. So going forward, right, there's a lot of future developments that we investigate. A lot of these are advanced lookup table implementations. Our work has shown that there's a lot of ways to optimize these lookup tables beyond metrics like mean square error. So if you know you're designing something for spectrum sensing and you care a lot about your dynamic range, you can optimize your spur-free dynamic range specifically with a lookup table design. A lot of it work also looks on reducing this memory constraint and implementation from this engineering standpoint rather than just theory. Some of our work involves optimizing dither distributions like we talked about for RF signals. Conventionally, dither has really been an audio processing application. So we're trying to take some of that existing methodology and apply it to these RF and MIMO applications. And then, like I talked a lot about optimal digital post-processing algorithms like interpolation and this injection of nonlinearity. How can we optimize the transfer function of ADCs to better model whatever we want to do? Basically, what I'm trying to argue is rather than taking ADC for granted as like just chip that you throw on, to a bigger part of a system, it's worthwhile to tinker with it and say, should we do it in low resolution? Should we optimize these transfer levels? Should we do something in the digital domain to get better performance out? And if you combine a lot of these techniques, you can actually get really, really strong performance even with low resolution, which, like I said, saves you a whole bunch of weight, power, cost, and area on the chip. So I think it's a worthwhile endeavor. And that's a lot of the research that we investigate. So going forward, I think this is, like I said, really practical for MIMO application. If you have 64 or 128 antennas, right, you might as well do it in 1 to 2 to 3 bits. Otherwise, you're never going to fit it on a chip. You're going to be restricted to these really big base stations with huge power consumption. But also even for things like ultra wideband, if you can get away with a good signal estimate with wide bandwidth with a low resolution, then you save a lot of time in the digital domain because your throughput in terms of bit rate is a lot lower. So if you have one bit per sample instead of 12 bits per sample, your whole digital end becomes a lot smaller. You save a lot in the modem. This is also really useful for direct sampling systems like software-defined radio, where people don't want to go through these intermediary steps. If you can get a high precision measurement and get away with direct sampling with the SDR, with the low resolution, it's beneficial. Obviously, this is a lot of this work is also applicable to other fields. So, for example, a lot of the fundamental work we do on dithering is really useful for audio processing and data compression and things like that. And then anywhere that you care about low power or low latency, it's worthwhile to investigate low resolution ADCs because they really present an easy way to crank out some extra efficiency. So this is really useful for low power stuff, mobile devices, wearable devices. And then in general, this is really fundamental test and measurement theory. So anywhere you do TNM, this kind of equipment is gonna make use of some of these results, especially the oversampling stuff. So yeah, we really want to acknowledge obviously my advisor, Professor Spasier, for all the support. And then our partners on the STTR project, which were Expedition Technology, and the 3 people with whom we work, and the Office of Naval Research for providing the funding. Thank you.
Yeah, a quick one, and I'm not an expert on this field by a long shot, but it's been on and off for a long time. Started with delta mode, dithering was one of the ways of exploiting delta mode. So there seems to be this non-trivial trade-off between super high speed, low resolution, but then you use a lot more silicon area, or you do parallel, flash ADCs, but you pay the price on sorry, that would be the high silicon area solution. The high speed is high bandwidth, and so I don't know how you do the currency exchange between silicon area versus bandwidth or speed.
Yeah.
But it seems that historically the low resolution approaches end up losing somehow.
Yeah, that's a great question. So this is, like you said, a long area of research. What happened is when ADCs first started getting developed, they were this flash architecture that you saw. And so the flash architecture is parallelized, right? Which you saw, it's just a bunch of comparators. And then people started looking at these sequential approaches, pipeline ADC, successive approximation register, and then lastly, sigma delta, which are really popular now, where you just have maybe one comparator, but you have to oversample by a really wide margin to use that one comparator and get a high resolution measurement. So what we look at is saying, if you really want to use a wide bandwidth application, you can't afford to oversample by a factor of 16 because you already want a bandwidth of, let's say, a gigahertz, right? So then you have to run at 16 gigahertz to use sigma delta. So we argue for really wide bandwidth, like you said, you have to use these flash architectures. But because of that, at high resolution, the number of comparators you need is 2 to the b, where b is your number of bits. So your area is enormous. For 16 bits, how are you going to fit 65,000 comparators on a chip and sample at 1 gigahertz to get the bandwidth you want? It's not really feasible. So that's why the low resolution ADC kind of fill this niche where you have to use a flash architecture because you really are restricted in your sampling rate. You want to sample very quickly, and you can only use a flash architecture efficiently if you have a very low number of bits. So with 3 bits, you can get away with just 8 comparators. Suddenly it becomes feasible to implement on a chip. And then, like you said, where ADCs with low resolution really start to lose is this distortion you introduce as a result. And then that's where we come in and we try to fix it afterward. So that's kind of the chain that I see is you start by restricting the bandwidth, then that restricts your architecture, and then that restricts your resolution. And then we try to fix it for that low resolution.
It's going to get very hot because we need to get ready for 1024 antennas.
Absolutely. Absolutely. And that's exactly why the funding that we get is for cryogenically cooled ADC, which is their solution.
In your hands.
Yeah. So that's exactly the project we're on is it got really hot when they tried to do it, and they put it at like 4 Kelvin and suddenly it worked. And that's where we come in.
Well, that's the physics.
Yeah. Yeah, it's superconducting, right?
So the goal is cost reduction.
The goal is cost reduction. Exactly. If you can do the same thing with lower cost using that.
Through cryogenic.
Oh, well, their issue is not just cost reduction, but it's very nonlinear. So they get all these spurs and all this distortion. They can't even use it right now. Right. So we gotta make it feasible at all. But they got the physicists, they didn't get the engineers on board. That's all we're here.
Did they get the accountants?
Yeah, I guess so. We got the
Yeah, a good thought. Very interesting. So typically, an ADC gives you 6 dB per bit.
Mhm.
So for a 3-bit ADC using your method here,
Yeah.
how much improvement do you get in terms of dynamic range?
Yeah, exactly. So the dynamic range, like you said, is typically limited to 60 dB per bit. So you would get if you look at those really coarse quantizations, you're limited to like 18 dB, right? And we call this, what we really care about is spur-free dynamic range, which is the difference between whatever tone or signal you're estimating and the highest spur, which sets the dynamic range of your system, which, like you said, is 6 dB per bit. So what we do is we found that we can get on average 10 dB of SSDR improvement across the bandwidth if you use, let's say, just a simple lookup table, not even considering these other methodologies. If you combine a lot of methodologies with specific signals of interest, you can get as high as 18 dB of improvement on top of the 18 dB of dynamic range you have. So suddenly it's like you have a 6-bit ADC out of a 3-bit ADC.
Yeah, I think this is very interesting. I know that we are looking at the power consumption for base stations and going also towards more and more RF chains and so on. And it's quite easy to do something with the analog part, switch off the microsleeve. But with the RF chain, it's always on kind of the sampling and the stuff. And I was wondering here if it's, have you looked at sort of maybe switching down to lower resolution when there is no load and when you don't need to send on very high bit rates, but then switching up?
Yeah, so there's a lot of research on what are called mixed resolution systems. So what people do is they have, let's say, a 3-bit ADC, and then in parallel, a 16-bit ADC. So maybe you turn on the 16-bit ADC for a little while to get a good estimate or to get a good characterization of your system. Then you switch to the 3-bit ADC for most of the time. So you can kind of modulate between the two. Or another example is if you have packets, right? Maybe for the synchronization step, you really need high resolution. So you turn on 16 bits for the beginning of the packet, get a good synchronization for your LO, which relies on some of these estimates for the equalization or for whatever these feedback paths use. Then you switch to 3-bit for the actual modulation, where you can recover the data easier. So you're right, it is an ongoing area of research where you try to modulate between high and low resolution. But our work is really fundamental on what do you do once you're in the low resolution state.
So for this example, so you're considering one RF chain for each antenna?
That's what they consider. This is a proposal I grabbed from online. A lot of proposals do this, right? I understand that there's some that combine them, right? Multiple antennas share the same RF chain.
Yes,
Sure.
Yeah.
But I'm saying for these in particular, you get really high scale performance.
Right, naive question, but is there any situation where if you knew the statistics of the signal, you would use non-uniform steps in the ADC?
Absolutely, yeah. So that's exactly what we talk about with the nonlinear quantization, right?
Okay.
This nonlinear injection. So if you know the distribution, you optimize exactly for it. So in the mean square sense, the optimal distribution, the optimal non-uniform quantization steps are called Lloyd max quantization. And that's been a form since 1960s. It's used for PCM and a lot of data compression and audio processing. But what we find is that if you specifically not just know your input distribution, but also some metric, like let's say you really care about bit error rate or you really care about EVM, you can even get more precise with your non-uniform step size and get even better performance. So I guess maybe it's a little hard to tell, but like these steps are a lot bigger than these ones, right? And that's kind of the idea.
That was hard to see.
Yeah, sorry, it's a little, right, it's garish with these colors. I know.
Okay, so thank you, Morriel.
Yeah, thank you.